What is up, you guys? Welcome to the 20th lecture of this course entitled Convex Optimization. In this one, we'll be talking about equivalent reformulations. That is, given an optimization problem, we're going to see how to derive equivalent problem to the original optimization problem, and we're going to take a look at the duals of those two equivalent problems. Are they the same or are they different? This lecture is going to give an answer and is going to show you different ways of achieving equivalent reformulations. That is, through introducing new variables to your optimization problem. We're going to be giving examples on how to do so, and we're going to be taking a look at the duals of each problem. We're going to see how to obtain an equivalent problem through transformation of cost. And when I say transformation of cost, I mean instead of maximizing or minimizing the cost that you have, you will minimize a proportional cost to it. That is, instead of maximizing exponential of x, you can maximize log of exponential of x. That is, you maximize an increasing function of the original cost. And last but not least, we're going to see how to formulate equivalent problems through implicit constraints. That is, if we have constraints to the problem, we're going to embed it or absorb it into the cost and define a new cost taking this absorbed constraint into account. That is, this cost is we're going to return the original cost when x respects this constraint, else we're going to return infinity. Okay? So without further ado, let's get started. Okay, so let's talk about the first type of reformulation. So such types include introducing new variables and probably some equality constraints. So let me show you what I mean through an example. Suppose that I have the following unconstrained optimization problem, that is to minimize, excuse me about my writing, my handwriting is not the best in the world, but bear with me. So minimize, I'm not going to say f0 of x, rather I'm going to say f0 of ax plus b. So what does that mean? Is that I've got a multi-dimensional function, so probably mapping, let's say, I don't know, as many rows of x, so let's as many rows of a, so let's say I've got m rows in a, and mapping us onto R. Okay. Well, a simple function could be f0 of x could be, I don't know, x transpose x, for instance. This is one choice. This is an example. But what we're doing over here is for any f0 of x and with no constraints. So this is the problem that I have, right? So a possible reformulation which turns out to be equivalent is to actually introduce a new variable that is y. So I'm minimizing this time. So f0 of, instead of ax plus b, I say y, and I choose my constraint to be y equal ax plus b. So subject to y equal ax plus b, right? So whether you're new to optimization, you have no background whatsoever, and you come and look at both problems, the first unconstrained one and the second one, which is an equality constraint problem, they are equivalent. You could come and without any background say, oh, those two problems are the same, right? All I'm doing is minimizing f0 of y on a straight line if m is 1, right? On a hyperplane is if m is 2, and you could see this as a minimization over an affine transformation, y equal ax plus b, right? So that being said, one might have the impression that both problems actually give us the same solution. Okay, so let's denote the optimal value of this problem by p star. So over here, the optimal value is P star. So what does optimal value mean? It means that the minimum of F0 over the feasible region. What is the feasible region or set over here? It's all Rm, because we don't have any constraints to define a feasible set. However, over here, stuff might look different. So you might say, oh, okay, so P star, if you want to denote it over here, it is the min of F0, but on this feasible region, right? Y equal AX plus B. So if you want to come and define your P star here, it might look different. Okay, you're going to start sensing or having an intuition that stuff are not actually the same. So why am I saying all this? Why am I talking about this? Is that my point here is that if we take a look at the duals of the first and the second problem, are they going to be the same or are they not going to be the same? That's my point of interest over here. So I'm going to denote the first problem by P1 and the second by P2, right? So in P1, if I take a look at P1, and I want to, compute the Lagrangian dual function, right? So what is the Lagrangian dual function? So in case of equality constraints, G of U is defined as the infimum over X of Lx, and the Lagrangian multiplier is nu, right? So what is the Lagrangian function of problem P1? If I want to define it, it is nothing other than F0 of Ax plus B, right? Because I don't have constraints, so I cannot come here so in other words, my constraints are 0. 0 equals 0, right? So I don't have constraints, so therefore introducing nu over here is completely useless. I don't have constraints to attach my nu's onto, right? So this is my Lagrangian function. Now if I want to come and do the infimum over X to get the G of nu, so infimum over X of F0 of Ax plus B, this is simply what? Since B is a constant, so you can say that it is the infimum of X over F0 of Ax, right? And since also A is a linear transformation, then you can go ahead and say it's the infimum of X of the function F0 of X. That is the min of the function F0 of X, which is P star, the optimal value. So this P star constant, P star, is your Lagrangian dual function. Okay? However, if you come and take a look at, so if I want to write down the Lagrangian dual problem over here, which is to maximize G, maximizing a constant P star, subject to positivity of nu, it's completely useless. You don't have nu to define, and you're maximizing a positive P star. So first of all, you don't have the nu's, and second of all, if you had the nu's, you could choose any nu because you're maximizing a positive quantity. So any nu should work out, right? So your Lagrangian dual problem over here is just to maximize a constant, right? Which is completely useless. Now, let's take a look at P2, problem P2, okay? Problem P2, on the other hand, tells us that so over here, what are my variables? That's one thing to keep in mind. It's of course X, the original variable of the problem, and the additional variable that I introduced, which is Y, right? So why am I writing this? It's really important so that you write down your Lagrangian dual function. in terms of the variables of the problem and the Lagrangian multiplier nu. So what is it? It is f0 of y, right? From what we know from previous lectures, plus nu star multiplied by the constraint, right? So it is ax plus b minus y equals 0. So I get an ax plus b minus y, right? So this is my Lagrangian of problem P2, Lagrangian function, of course. And to obtain the next step, before going to formulate the Lagrangian dual problem, I need the Lagrangian dual function g of nu. So what do I do over here? As I did in P1, I find the infimum, but this time over two variables of the problem, x and y, right? So infimum over x and infimum over y of L of x, y, and of course nu, right? So this is what I should do. Now replacing what I have, that is infimum x, y of this quantity over here, that is, let's rewrite it again, f0 of y plus nu transpose ax plus b minus y, right? So what does that mean? First of all, I need to, since I have two variables, you can either do it jointly, right? You can either do this infimum jointly, or you could choose to do the infimum over one variable and then do the infimum over the other variable, which is what I'm going to do. So first of all, why am I going to do this? Well, for x, we have one term that depends on x. So the infimum over here is easily done, right? Why? Well, first of all, what is the infimum over x? So let me write this in a more friendly way. First, let me expand this. So infimum of xy, f0 of y, plus nu transpose. So I'll leave b minus y post multiplying nu transpose. So I have my b minus y over here. And I'll extract, or I will isolate this term, nu transpose ax, right? So nu transpose ax. Okay, so this is the only term that depends on x. So why not do this? First, an infimum over y, right? And then an infimum over x of the same quantity, right? So which is f0 of y plus nu transpose b minus y plus nu transpose ax, right? Okay. Again, since this is the only term depending on x, that means that the infimum with respect to x is only applied on this last term. And thus, what I get, let me just get there first of all. So, plus the infimum of x of the term nu transpose ax. Correct? Correct. So I ask and I answer myself. Anyways, so what is the infimum of this term? It's clearly, you can choose x to be a multiple of, I don't know, minus infinity. So you can choose x to be a vector containing minus infinities, right? Or at least one term containing minus infinity, given that any other term is not plus infinity, so that they don't like give us an undetermined form. So with that said, this infimum could be minus infinity except under one condition. And what is that condition? Is that x falls in the null space of A. We did that thing before previously in my previous we did a similar thing in my previous lectures where we were computing an infimum of a similar quantity. So I believe it was infimum of x transpose multiplied by y, something like that. Or yeah, something like that. Or something like infimum. Well, in that case, it is minus infinity, except for one case where y is 0, right? That's the only case where the infimum becomes 0. Only when y is 0, right? So in case of the more general case, which is x transpose A multiplied by any other vector, I don't care, B. So this thing is minus infinity except for one case which is when AB is 0, right? Because, or in other words, when B lies in the null space of A, right? AB is 0. Well, we will be interested in such a case because guess what? When nu transpose A is not 0, that means this thing is minus infinity. And then when you go back over here, G of nu, you're going to have to maximize this thing to formulate the Lagrangian dual problem. And it's not interesting because you can. What's the point of maximizing minus infinity? There is nothing to do, right? So we're going to include in. So let me go back down here. So let me denote by D2 the dual of problem P2. Okay. So if I were to formulate the problem, which is in the end, of course, is going to be maximize this term over here, the Lagrangian dual function, I'm going to leave this as is because I don't know what I'm going to be maximizing in the end with respect to nu. But what I do know is that, while I was deriving the term of g of nu, okay, I paused at a place and I enforced or I imposed the constraint that, nu transpose A is 0 or nu transpose A is 0, right? So why am I doing this? Because this term, I don't want this term to go down to minus infinity. Instead, I'll keep it well controlled at 0. So that being said, my Lagrangian dual function becomes the infimum of y over the term f0 of y plus nu transpose b minus y, right? Okay, looks good. Now, to finalize, let me fix that transpose over here. I don't like how it looks like. So this is a transpose. This is a b minus y. Okay. Now the infimum over y of this term is also easily achieved. Well, how do we do that? Well, first let's isolate terms that do not depend on y. Let's do that. Okay, going down here. So it's the infimum of y of the term f0 of y. Well, the nu transpose b does not depend on y, so I will isolate it outside as such, right? And I'll keep the term nu transpose y, or correctly speaking, minus nu transpose y, right? So, okay, does this form remind you of something? When you're trying to find the infimum of a function minus an inner product of the variable and another arbitrary vector? Well, let's go back to previous lectures. And if you take a look here, when we were talking about conjugate convex functions. So over here, we have this nice looking function that is the supremum, okay, not infimum, supremum of the inner product minus the function in hand. What we have here is the infimum of minus this whole thing. So if I extract the minus outside, right, I get a supremum. So what I mean is this. Instead of an infimum, I could write this as minus the supremum, the sup of y of nu transpose y minus f0 of y, right? plus mu transpose b. Why did I do that? Well, I could express this whole thing in terms of the conjugate function of f0. That is, minus, this thing is defined as f0 star of the arbitrary vector, nu, plus nu transpose b. Okay? Now this is the simplest form you can write this term down. So this is my g of nu. And by the way, why do we write it in terms of conjugate functions? Because, you know, you can always, depending on the form of f0, you have a corresponding conjugate function. So going back here, we saw some examples like when f of x is the absolute value of x, or when f of x is 0 except for 0 when, you know, so when my cost is the absolute value of x, this is the associated conjugate function. It is 0 between minus alpha and alpha, or minus 1 and 1 in this case, and infinity elsewhere. We saw other examples, for example, when f of x is log 1 over x, then the conjugate function would be minus 1 minus log of minus y when y is negative, and infinity elsewhere. We gave interpretations of conjugate functions when, you know, we said that, okay, so for every, since y over here is, if you look at this thing in 1D, you don't have a transpose anymore. You have a yx minus f of x, all in 1D. Y is 1D, x is 1D, and of course f of x is 1D. So in this particular case, we saw that, oh, the conjugate function is nothing other than a function of the slope of the difference of the straight line. So varying the slope of this line, this is y, right? Y would be the slope of the line yx. And we're measuring actually the distance between a straight line and the actual function. We're taking the supremum actually of this distance. So when they're parallel, the distance is the distance. You just draw in a, you know, a perpendicular line, and you know, you can measure the distance of the between the intersecting points. And when they're not parallel, when it's something like this, you say, oh, okay, if my domain of f is everywhere, this supremum is, you know, it's diverging. So the supremum is infinity, right? And that's why, which explains the infinity over here. Okay, going back to our lesson. So what we're doing is maximizing minus f0 star of nu plus nu transpose b, subject to nu transpose a equals 0. Now taking a look at this Lagrangian dual problem, D2, and its equivalent dual, which is P star, or where is it? Maximize P star, this is D1, if you will. They're completely different. It's not the same problem, and they give different solutions. Over here, there is no nu to start with. And over here, the nu is, I don't know, it solves this problem, right? So that said, the dual of this reformulated problem, D2, is very different and indeed more useful than that of D1. Okay? So here is a simple example of when, you know, I introduce a simple variable to the problem which is not altering the problem in any way. It's just, you know, replacing ax plus b by y and enforcing this variable introduction as a constraint to the problem. So this is one example, and actually one really important example, to see that if I have two equivalent problems, then their duals could be completely different. Let's see examples on that. Let's see applications of, when I say examples, I mean applications on different forms of f0. So let's see what I mean. Let's, for example, take this problem. So as before, let's denote this problem by P1, okay? And let's formulate an equivalent problem. That is, instead of my affine constraints, AI transpose X plus BI, I'm going to denote this as YI, okay? I'm not going to write this YI on top over here because you might think, oh, this is associated with P1, but no, it's associated with P2. So for that, I'm going to say, oh, P2 is actually to minimize the log sum of exponentials of the form yi, okay, where I goes from 1 till m, right? Subject to yi's equal to AI transpose X plus BI, where I've got I going from 1 till m, right? Those are my constraints. Well, those are affine constraints, and if you look closely, you can actually see that I can write all this guy over here as one constraint, that is, or one big constraint in a compact way, I mean, as y equal to ax plus b, okay, where y contains yi in its ith entry, b contains bi in its ith entry, x is x, it's a vector, and AI transpose is actually in the ith row of the matrix A. So A looks like this. A1 transpose down to AM transpose. Okay? So I'm going to erase this and replace it with this. Alright, good. So from what we saw in the previous general example, if you will, for any f0 of y, this applies. So what I had first is the unconstrained problem, f0 of ax plus b, right? In this case, f0 is of the log-sum-exponential function, right? Log-sum-exponential, this is my f0. And so if I were to write the dual of the first problem, it would be only to maximize p star, which is the optimal value of the problem, maximize p star. Now, this is why we're not going to write down d1, we're going to instead write down d2, the dual of p2. So d2, in this case, from what we know from the previous example, is this. So I'm going to copy paste this, where f0 again is the log-sum-exponential function. And we know from previous lectures, if you go back to in particular, if you go back to my lecture that talks about conjugate functions, you will see that we actually derived an expression for f0 star when f0 is the log-sum-exponential function, which takes the form sum of nu I log nu I going from 1 till m under two conditions. The first one is that nu is entry-wise positive, which makes sense because we've got a log of something. So this is 1. And 2 is that all my nus should sum up to 1. That is 1 transpose nu is 1. Else it's infinity. So of course we're not interested in the infinity case because there's nothing to maximize really. So we're going to be interested in this case, and thus we will replace this expression over here and add its corresponding conditions as constraints to the problem. So with that said, we will have that I have a sum nu I log nu I, so sum I going from 1 to m nu I log. Let me make some space over here, it's really annoying. So minus sum I going from 1 to m nu I log nu I. Okay. And also we will be adding those two as constraints. So the first constraint is that nu is positive, and the second one is 1 transpose nu is equal to 1. And the point here is that D2 is very different from D1, which is just to maximize a positive. That is this, P star, which is the optimal of the problem. It is, so D2 is not only different than D1, but it is also more useful because there's actually something to maximize over. Okay? Oh, and by the way, this is a GP. It's a geometric problem. Okay? What are GPs? We talked about this in previous lectures. So GPs look like this. You're minimizing a polynomial, not a polynomial, a polynomial. So what are polynomials? They are, so polynomials are additive in different powers of the problem, the variables of the problem, whereas polynomials are multiplicative, and the coefficients are taken as powers of each variable. So it's c x1 alpha 1, x2 alpha 2, down to xn alpha n. Now the log-sum exponential function is not directly a polynomial. You need to do a change of bases in order to see that. We talked about this over here, I believe. Yes, over here. As you can see, we've got a sum exponential, right? We said that the sum exponential could be, if you go back over here in the steps, it's a polynomial. We took this as change of variable. Each xi is exponential yi. And in this case, you can see that the sum exponential is a polynomial, okay? So this is one example. Another really interesting example over here could be when you're minimizing a norm. This is more ubiquitous, I would say, because everyone has seen this problem at least once in their career. So minimize the difference of norm of ax minus b, of course with respect to x, and the norm over here is not necessarily the Frobenius norm. It could be any norm. It could be the atomic norm, the zero norm, whatever norm, I don't care, the L1 norm, I don't care. The point here is that we're minimizing a norm. What is the norm? I don't care. Okay, so here we can reformulate. So if we denote this as P1, we can reformulate P1 as a problem P2, where I am minimizing the norm of y, where y is my ax minus b. And of course the minimization is with respect to x and y. So subject to y is ax minus b. Okay, so as before, D1 is an unconstrained problem where the job here is to maximize p star, a constant. Whereas over here, it is to, as we did previously, we are maximizing this term over here, this problem over here. So what is my f0 star over here? Okay, so now all we need is to express the conjugate function f0 star nu, right? So how do we do that? Well, note that my f0 of x initially is the norm of x, right? So my job here is to find f0 star of y. What is it? So in other words, I am looking for the dual of the norm, right? So by definition, f0 star y is the supremum over x of y transpose x minus f0 of x, that is the norm of x. Now we have two cases here to argue based on the dual norm of y. So the dual norm of y, by definition, let me write that down here, and we will denote it as the norm subscript star. That means the dual norm of y. It is the supremum of y transpose z, of course supremum over z, on the unit ball. So when the norm of z is less than 1. I can also express this in terms of x instead of z, because we've got a y transpose x. So I can write down supremum with respect to x of the term y transpose x on the unit ball. This time the norm of x is less than 1. Okay. Now, it turns out that if this term over here is greater than 1, then we have a condition right here. We can argue one case. And what is this case? Well, if the dual norm of y is greater than 1, or in other words, if this term over here is greater than 1, this means that there is a, well, now I have to use a z because I can't use the x. We have an x over here. So there is a z in Rn such that this thing is greater than 1 because the dual norm is assumed to be greater than 1. So y transpose z is greater than 1, but z is within the unit ball. So z is less than 1. Of course, because the dual norm is greater than 1. So the term that is the supremum is also greater than 1 under the unit ball constraint, right? So over here, if I choose my x, because I want a link between this statement over here and the term I'm finding the supremum of. So we said that there exists a z, right? So if I pick my x to be a multiple of this z, So if I say that, choose my x to be alpha z, right? Where alpha is an R. Then what I get is this term that I'm finding the supremum of becomes y transpose alpha z. So my alpha is a constant, is a scalar. It could be extracted to the outer left. So y transpose z minus, and here since this is a norm, then alpha x becomes the absolute value of alpha times the norm of x. So if I choose my alpha to be positive, it will be an alpha times the norm of z, right? Which is alpha y transpose z minus z. Why did I do this? Well, it's to ensure that this thing is not only not zero, but positive. Because y transpose z is greater than 1 and the norm on z is less than 1. Okay, so this thing is ensured to be greater than or equal to 0. Okay, and if I let my alpha go to infinity, so as alpha goes to infinity, this term goes to infinity as well. So it scales with alpha, in other words. Okay, what does that mean? It means that my conjugate function is actually when the dual norm on y is greater than 1, which is the case we just argued right now, then the conjugate is infinity. Okay? As we got over here. Now, in the other case where the dual norm is less than 1, now there is a trick that we're going to use here. We're going to rewrite the dual norm in a different way. That is the y transpose x. So y transpose x. Be careful, when I say that the dual norm is less than 1, it doesn't mean that y transpose x is in general less than 1. That's not true. It is only true if x is within the unit ball. So this thing is less than 1 only if the norm of x is less than 1. Keeping that in mind, y transpose x for any x, not necessarily less than 1, not necessarily with bounded norm or norm unit ball norm, right? Could be written as if I multiply and divide by the norm of x. So I multiply by the norm of x over here. And then I get a y transpose, then x divided by its norm, right? As such. Now I can say that this term over here is actually upper bounded by the dual norm of y. In other words, this is less than the dual norm of y. And why is that? Well, because this term is of the form y transpose z, right? So this is of the form y transpose z, where z is x over the norm of x, and hence a norm of 1. A norm of 1, that means y transpose z, given the constraint on z, that is the norm of z is less than 1, falls within this set over here. So if I'm taking the supremum, or in other words, I'm looking at the dual norm, that means, of course, I am upper bounding this term, because this term is actually the sup of this quantity over here. Okay, so we can go ahead and say this is upper bounded by x multiplied by the dual norm of y. Okay, and why is this useful over here? Well, if the dual norm is less than 1, then I can go ahead and say if I take a look at this inequality, of course, I can go ahead and say, okay, since my y transpose x is less than the norm of x multiplied by the dual norm of y, then I can go ahead and use this condition over here, that is the dual norm of y less than 1. I can go ahead and say this guy is less than the norm of x. Why is this useful? Well, if I take a look at what I'm interested in, that is the sup of x of y transpose x minus the norm of x. Well, in this particular case, where the dual norm of y is less than 1, guess what? This term is negative. Why? Because y transpose x is less than the norm of x. So y transpose x minus the norm of x is negative. Okay? So what does that mean? Why do we care? Since we're finding a supremum of a quantity that is non-positive, okay? It turns out that the supremum of this guy is attained when x is 0. So when you choose x to be 0, you attain the maximum, that is 0. And hence the sup in this case of a non-negative term, which is attained when x is 0, is 0. Okay? So going back here, the conjugate function of the norm, the conjugate of the norm is 0. Only when the dual is less than 1. Now, what kind of interpretation can we give here? Well, if you take a closer look on the conjugate function of the norm, right? It is an indicator function, so it's either returning a 0 or an infinity, right? It's telling us something. It's telling us, oh, I'm going to be 0 only when the dual norm of y is less than 1. And it's infinity if the dual norm of y is greater than 1. So if I were to, on a simple xy axis, but where the x-axis is the dual norm of y, right? And the y-axis is the conjugate function, which I'm interested in. Then if the dual is, well, here minus and negative values don't count. We don't care about negative values, right? It's a norm. So what I care about is the value 1. When the norm or the dual norm is less than 1, I am 0. Else I'm going to explode to infinity. Or to be more specific, it is an indicator function of the dual norm unit ball. So this is not any unit ball, it's a dual norm unit ball. It's a unit ball defined in dual space. Okay, good. Now why did we do all this? It's just to get the form of the conjugate function to use it over here, right? So replacing this over here, I don't care about the infinity, because I don't want to maximize a term that contains infinity. No, I'm going to be concerned with the other case when it's 0. So replacing this and taking the dual norm condition into account, d2 could be rewritten as maximize with respect to nu if f0 star, if the conjugate is 0, then I don't have anything here. I'm left with nu transpose b, right? Subject to my constraints, the first one being the affine mu transpose A equal to 0, and the second one is the dual unit ball constraint. So my y here is the nu, because I'm taking a look at f0 star of nu, right? So replacing y by nu, I get that the dual norm on nu is less than 1. And that's it. So moral of the story, d2 is different than d1. Okay? Now we can also introduce new variables not only on the cost function but also on the constraints. So let's say I've got a problem of the following form, that is to minimize the cost f0 of a0x plus b0 subject to fi aix plus bi is less than 0, right? Let's say I've got the following problem and my AIs are in RKI by N and my FIs are mapping RKI onto R and they are convex. Okay? All my FIs are convex. Okay. So as we did previously, we can introduce auxiliary variables, yi's, replacing all terms that contain aix plus bi. So instead of P1, I will have problem P2, that is, instead of, as we said, aix plus bi, I've got yi's, right? And instead of a0x plus b0, I've got a y0, where all my yi's are aix plus bi. And I've got how many terms? I have got m plus 1 terms, 0 down till m. 0 is for the cost, 1 till m are for the constraints, right? Okay. Now the Lagrangian, if I write down the Lagrangian of P2, it is, now be careful, over here I'm minimizing with respect to x and y. Y contains y0 down to ym. So I've got x, y, lambda attached to the inequality constraints and nu to the equality constraints. So I've got my cost f0 of y0 plus a sum on terms lambda I multiplied by the ith inequality constraint, that is f I yi plus a sum on the equality constraint, so nu I multiplied by ax plus b minus y, so ai x plus bi minus yi. Okay, I going from 1, or in this case 0 till m, and over here from 1 till m. Okay, now the next step to write the dual problem is to find the dual function, that is g lambda nu, that is defined as the infimum over x and y of the Lagrangian function L xy lambda nu. So if I am finding the infimum of the Lagrangian function, let us replace this whole term over here. We get this whole term. Now, as we did previously, let's start over the easier term, that is x, because it appears once over here, or more generally speaking, we have a sum term over m plus 1 terms containing x. Okay, now to do this, I'm going to isolate first the infimum over y, and got f0, y0 plus sum I going from 1 till m, this term, lambda I, fi, yi, plus this whole term except the x, because I'm going to isolate it to take the infimum over x to it. So sum I going from 0 till m, nu I into bi minus yi plus infimum over x of this term, which is, notice that x is common in all the sums, so I can extract it outside as such. So sum nu I, oh, this is a nu I transpose, I'm sorry about that. This is a nu I transpose. Okay. So nu I transpose AI, all this term multiplied by x. So what is the infimum of this term? It is, of course, minus infinity in the general case if this term is not 0, else it is 0. So we're not going to be interested in the case where this whole term is pulled down to minus infinity. No, we're going to take the case where this guy is 0, okay? So the dual problem will have to impose this constraint somewhere, right? So if I go ahead and say subject to, I'm going to have to impose that the sum on nu I transpose AI is 0, right? Where I is going from 0 till m. Okay, good. So I got rid of this term, it's 0, and now I'm left with infimum of y of everything else. That is f0 of y0 plus the sum I going from 1 till m, lambda I, fi, yi, plus the sum from 0 till m, nu I transpose bi minus yi. Okay? Now let's extract terms that do not depend on y, which is this term over here. Let's extract it outside. So we get a sum from I going from 0 till m of this term that does not depend on yi's plus the infimum of y of f0 y0 plus the sum on lambda I fi yi plus the sum on nu I transpose yi, or this is a minus because we have a minus over here. So a minus. And so how can we, look at this infimum? So notice here that I'm going to divide this whole term in terms of the cost functions. So f0, y0 is actually attached to nu0 transpose y0. f1 of y1 is attached to nu1 transpose y1, and so on. So with that said, if I isolate y0 first, that corresponds to the cost function, I get f0 y0 minus nu0 transpose y0. And then for all the others, I get all the others are the same. They're all multiplied by lambda I. Let's say it's as such. We take the infimum. So I'm going to extract lambda I. That's what it is. Fi yi minus nu I over lambda I. Lambda I is a scalar, nu I is a vector. So this thing transpose multiplied by yi. Okay? This infimum is with respect to yi, and I'm summing from 1 till m. Okay? Now, why did we write this? It's because each term looks the same, almost the same, right? And it is actually, this guy, as we saw previously, is the conjugate of f0 of nu 0. So this is actually minus. We should write minus, because minus supremum, flip those two terms, then we get the conjugate function. So f0 star of nu 0 minus sum, same thing over here, from I going from 1 till m, lambda I, fi conjugate, but this time my variable is not nu I, it's nu I over lambda I. Okay. Now, if we take a look at this expression over here, if we take a closer look, it is concave in the dual variables. So this last expression is what I'm going to maximize in the dual problem. So maximize with respect to lambda and nu, this whole term over here, which is the sum I going from 0 till m, nu I transpose bi minus f0 conjugate of nu 0 minus sum on lambda I fi conjugate of nu I over lambda I. Where I is going from 1 till m. Of course, I've got an additional constraint, that is lambda is positive, entry-wise positive. We always do that when we've got inequality constraints. Lambdas are attached with it's always the Lagrangian multipliers attached with the inequality constraints are subject to be positive, okay? Now, of course, some of the lambda i's are turn out to be 0, in which case the nu i's will be non-zero. In this particular case, if this nu I is not 0, then what happens? Now take a look at the denominator. If this is fi conjugate of 0, then you're taking the conjugate of infinity. And this thing will blow to infinity, to minus infinity. We've got a minus sign, so minus infinity. Now on the other hand, if lambda I is 0 as well as nu I, so you've got it 0 over 0. However, this term over here is 0. This will force this indeterminate form to be 0. All those terms are 0. Okay? It's always good to see what happens in such extreme cases. Okay, so here we saw that indeed we can apply the same approach when applying change of variables on not only the cost function but also the constraints of the problem. They could also be applied to equality constraints as well, of course. But in this example, we showed how to do that on inequality constraints. Okay? So this is it on how to, deal with equivalent problems by introducing new variables to the problem. Now, of course, there's other ways of formulating equivalent problems, such as you could transform your cost. So the cost function, you can actually transform it to something that is proportional to it. Like if you're maximizing, let's say f0, and you're maximizing f0 square, intuitively it's the same thing, because if you maximize an increasing function of the cost, then you're maximizing the same thing. In other words, let's say you're maximizing, I don't know, EX, right? EX looks like this. But where X is between, I don't know, maybe 1 and 2, it's the same as, maximizing an increasing function of EX. Let's say, for example, log. Log is increasing. So if you take the log of EX, then you're maximizing X. And X would look something like this, right? So maximizing an increasing function of the cost is the same, intuitively speaking, as maximizing the cost. But what happens in such cases? As we saw before, the dual problem of such transformations could turn out to be very, very, very different. And let me show you an example. So let's say I am back at the norm minimization problem that is unconstrained in this case, ax minus b. Okay? I'm minimizing with respect to x. Now over here we saw this exact example, the unconstrained norm minimization problem. We just saw that if I introduced my y variable simply by saying my y is ax minus b and imposing that as a constraint, we saw that the dual is actually this. So I'm going to keep this over here. So we just saw that the dual of this problem, of this norm minimization unconstrained problem, if I choose y is ax minus b, and then I impose this as a constraint, we saw that the dual, d2, is actually this problem over here. Now we're going to see what happens if I don't want to minimize, the norm of ax minus b by saying y is ax minus b, and then imposing that as a constraint. No, instead let's formulate P3, that is. So instead of just saying, oh, I want to minimize y, where y is ax minus b, I want to minimize y squared. So intuitively speaking, we're doing the same thing because we're minimizing an increasing function of the original cost, right? But let's take a look at the dual. What happens over here? What is the dual of this problem? So what is the dual of this problem? Of course, it is D3, where my job is to maximize with respect to the dual function of the problem, that is g of nu over nu, right? Now what is g of nu? First we need the Lagrangian function, that is L x y nu, that is the norm on y square minus nu transpose multiplied by y minus ax minus b becomes a plus b, right? Okay, now if I take the infimum, so g of nu is the infimum over x and y of L x y nu. First, let's take the infimum over x. So it becomes a y square minus nu transpose y plus b plus infimum over x of nu transpose ax, right? Now, if I want the infimum of this guy, it's minus infinity, but I will be interested in the particular case where nu transpose A is 0, and hence I will be imposing it as a constraint on the dual problem. So that said, this thing is 0. And I'm left with this guy. Now, since we have an infimum with respect to y, it's better to isolate nu transpose b, right? So actually I have a minus sign here, which is inappropriate. This should be a plus, and this should be a plus, and this should be a minus, right? Okay, so I get a, so let's isolate the term that doesn't depend on y, which is mu transpose b. We get mu transpose b plus infimum on y of y square plus nu transpose y. Now this is actually the conjugate, but there's a minus sign. So if I put here a minus, so let me rewrite this in another way. Nu transpose b plus infimum on y. If I put here a minus y squared, it's the same thing. This minus cancels with the square. Actually, the norm on a negative is the same as the norm, so nothing fancy here. And over here I say a minus mu transpose multiplied by minus y. So now this looks like the conjugate function, so we get mu transpose b minus, so that this thing becomes a supremum, and we get the conjugate function on nu, right? Square. So now this is my g. So over here, this is what I get. And the point here is that D3 is different from D2. Okay? We have this additional norm popping up over here. Okay? And of course, we don't have this unit dual norm constraint. Okay, so we showed an example where transforming the cost could, of course, even though you have an equivalent problem, the duals will look different or will be different. Okay? One last thing I'd like to talk about is implicit constraints. Okay? And what are implicit constraints? Well, it's when you make your explicit constraints implicit. That is, it's when you impose, it's when you change the constraint that you have and make it part of the domain of the objective. Let me show you an example. So let's say I've got a linear program That is, I'm minimizing C transpose X subject to Ax equal to B. And we're going to impose one more constraint that is known as the box constraint. That is, X is bounded entry-wise between two vectors, lower and upper. Okay? So this is also known as an LP with box constraints, or a linear program with box constraints. Of course, L is entry-wise less than U. So given L is less than U, let's call this problem P1. And let us replace those two constraints. We're not doing anything here. We're just saying X between L and U. We're going to write it as two separate inequality constraints, where the first one is X less than U, and the second one is minus X less than minus L. Okay? So those two replace the box constraint. Now the Lagrangian function over here is Lx lambda nu. That is actually, we can split lambda to be a vector containing, lambda 1 associated with the first inequality constraint and lambda 2 associated with the second inequality constraint. So we can write this as C transpose X plus nu transpose AX minus B, that's for the equality constraint, and plus minus lambda 1 transpose plus lambda 1 transpose associated with the first inequality constraint, that is X minus U, plus lambda 2 associated with the second inequality constraint, that is minus X plus L. Right? Now let's do the infimum over X to get G lambda nu. So it's the infimum over X of all this thing so let's grab all terms that depend on X. So we've got C in the first one plus nu transpose A, that's over here, plus actually this is a C transpose, plus lambda 1 transpose, that's over here, and minus a lambda 2 transpose, all multiplied by X. That's the infimum over here. And we isolate all other terms that are minus nu transpose B, that's over here, minus lambda 1 transpose U, that's over here, and plus lambda transpose 2 transpose L, that's over here. Now taking a look at this infimum, we can pull it down to minus infinity, but we don't care about that. We care about the particular case where this whole vector is 0, right? In which case the infimum becomes 0. So if we impose that all this guy is a 0, if I were to write D1 problem D1, I would have to impose this constraint. So C transpose plus mu transpose A plus lambda 1 transpose minus lambda 2 transpose is 0. Okay? Of course, I'm going to maximize here the resulting Lagrangian function with respect to mu and lambda, where lambda is lambda 1, lambda 2. And since I imposed this constraint, this guy over here is 0, and I'm left with this part that is minus mu transpose B minus lambda 1 transpose U plus lambda 2 transpose L. And of course, the Lagrangian multipliers associated with the inequality constraints should be constrained to be positive. That is, lambda 1 is positive and lambda 2 is positive. So, for this problem where I did not do any transformations or introduce any variables, this is the dual. Now, let's say I am going to be interested in an equivalent problem, P2. So this is an equivalent reformulation of P1. But instead, I'm going to absorb this constraint into the cost. What do I mean? So let me show you. Instead, I'm going to be minimizing a function of x, so f0 of x, subject to the remaining constraints that is ax equal to b, right? Where my f0 of x is defined as follows. So if I respect this constraint that I absorbed into the cost, if I respect it, I'm going to return C transpose. So it is C transpose x only when x is or lies within the box. Else it is plus infinity. Okay? So to me, P2 is the same as P1. Well, let's take a look at the dual problem. As we did in all the problems, to get D2, I need to pass by g of nu, that is the infimum of the Lagrangian function. So the infimum over x of f0 of x plus nu transpose ax minus b. Now, since f0 of x is a finite only when x lies within the box, then it's the same as taking the infimum over that box where I have a finite quantity, C transpose x. And the rest remains the same, ax minus b, which could be written as, if I isolate terms that do not depend on x, so I've got this nu transpose b with a negative sign, so minus nu transpose b plus the infimum over x lying in the box of the term C plus A transpose nu, all transpose multiplied by x. Okay? Now over here, I don't need to argue that this thing could be pulled down to minus infinity. Why? Because x lies within a box, within a finite box. So I don't need to argue the case where c plus a transpose nu is 0. No, I don't care about that. Actually, what happens over here is that we have two cases. If I take a look at the ith constraint of this, problem, of this term, which looks like this, maybe, c plus a transpose nu. So I'm taking a look at the ith term of this vector multiplied by xi, and I'm trying to find the infimum of this guy where xi is between li and ui, right? So what happens over here? We have two cases. If this guy is positive, so if c plus a transpose nu of I is positive, then what is the infimum over here? You could choose xi to be li, right? So in which case you get c plus a transpose nu I multiplied by li if this term is positive. Now, if it's negative, you wouldn't want to choose the li. You'd want to even lower it down even more. So over here, you'd want to choose ui, right? So you'd get a c plus a transpose nu I of ui, right? So you can combine both conditions in one equation. You could say that, okay, so I'll choose this guy if this part is positive, else I'll choose this guy. How can we combine both in one equation? Well, you could introduce the max-min operator. So you can actually say, okay, so if this guy, the max of c plus a transpose nu I and 0, which is the max, if it's this guy, then return the max. So max of c plus a transpose nu I and 0 multiplied by li, that's the first term. Now if it is lower, it is 0, and hence this term is gone, right? Plus, you do the same thing now for the negative term. You take the max, or now you take the min, because it's negative, between c plus a transpose nu I and 0 multiplied by ui. So now, if this term is negative, then we're going to choose this term. And what happens to this term? Since this term is negative, then what is the max? It's 0, and hence this term is gone. We're left with this guy, which is this guy. And when c plus a transpose nu of I is positive, then this term is chosen. And what happens to this term? Since it's positive, then what is the min between c plus a transpose nu of I and 0? It's 0, and hence this term is gone. So we can define an operator over here, that is max min, and we can also generalize this to a vector notation, entry-wise. So we can write this down as minus transpose b plus I don't know what you want to call this. Let's call it max between, if we want to generalize it to the vector case, let's call that max of C plus A transpose nu and 0 all transpose multiplied by L plus the same thing but a min this time. So min of C plus A transpose nu 0 transpose U. And note that if you zoom in on the ith constraint, only one is active. You can't have both active at the same time. You can leave it as such, no problem, but it's more easier to deal with this because I can go ahead and write it in the dual directly. So in the dual, I'm going to maximize this term. So my D2 now would be to maximize this. So maximize with respect to nu. This is an unconstrained problem, and this is my D2. Okay? Now, moral of the story, D2 is very different from D1, where we only absorbed. So over here we absorbed, we did, if you will, we did the opposite operation of introducing variables. No, here we absorbed a constraint into the cost, and we took a look at the dual, which is D2, and it turned out to be different, actually very different from D1. And that's about it. So this is it for this lecture. We did a lot of stuff in this one, which all deals with equivalent reformulations. So in this one, we talked about 3 equivalent reformulations. The first one is by introducing variables either to the cost or to the constraint of the problem as such. We gave some examples on, and to be more specific, we gave examples on the log-sum-exponential cost, the norm minimization problem. So that's for the first way of doing equivalence reformulation. It's through introducing variables to the problem. The second way is transforming the cost into something that is proportional or an increasing function of the cost. We saw that indeed, of course, duals of those 2 equivalent problems turn out to be different. And the last way is by taking into account implicit constraints. That is, we modify the cost function to be infinite when the constraint is violated. And we saw indeed that if we do such equivalent reformulations, the duals could also turn out to be very different. So thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below and I'll be happy to respond as soon as possible. We'll also go ahead and check out my new website, that is bazziahmad.com, where I'm going to be updating it from time to time. I'm going to be leaving lecture notes, and I'll see you in future lectures.